thank you for coming back on time and for joining us for the lightning talk sessions. So, as I said before, these are talks by Australia's or Australasia's next generation of HPC leaders, and I'd like to start the 3-minute talk sessions now.
Hi everyone. My name's Helen. I'm from the University of Sydney, and I'm going to be presenting on a project where...
Yeah, you might have to stand here.
Oh, I can see this. For identifying novel inhibitors against herpes simplex 1 virus. And currently all the drugs which are used to treat HSV1 target replication of the virus. So with this project I aim to target a surface protein called GD, which is used in binding of the virus to human cells. And so that's involved in entry. And my background is in molecular biology, so I've spent a lot of time pipetting in the lab, so I'm very drawn to any method that can reduce that experimental time. And that's where the computational side comes in. So I started with a database of compounds, and I filtered them for favorable properties, and in particular looking at properties that are associated with inhibitors of protein-protein interactions, as that's the type of interaction I was looking to block. And these properties are actually quite distinct from typical drugs. And then the next stage was to use molecular docking to predict the binding affinity of all the filtered drugs against the target protein GD. And with molecular docking, one of the main steps is to select an area of your protein and define the dimensions where you sample the binding of your drugs. Typically, if you're doing a screen with a set of drugs, you keep the search space static, but I used a slightly different approach where I allowed the search space to be adjusted a little bit for each drug based on the radius of gyration. And this has been shown to actually increase the accuracy of docking, and it also creates a balance between computational time. So you don't use excess computational time for the smaller ligands. And whilst I only screened 30,000 drugs, this can definitely be upscaled to millions of drugs. And then after this, 20 highly ranked compounds were selected and purchased and tested in the lab against live HSV1 virus. And one compound, compound number 34, showed antiviral activity in the micromolar range, so it had over 80% inhibition of infection in the micromolar range. And when the drug was introduced at different time points over the course of infection, we found that when the drug was pre-incubated with the virus, it was blocking infection, but not at the other time points. So it's nice that's consistent with the predicted docking mechanism. Yeah, that's all. So if you have any more questions or comments, you can come find me at the poster presentations. Thanks.
Perfect timing.
Okay. Hello everyone, I'm Shunjiro Tomura. I'm doing a PhD at the University of Queensland, and I'm also a member of the ALCS Center of Excellence for Plant Success in Nature and Agriculture. And my poster is about GPU can accelerate the prediction of complex phenotypes. But before I start explaining about this, let me introduce about my research background. I'm doing a genomic prediction, which utilizes the genetic information to predict the phenotypes of a trait of plants. For example, we may want to predict the leaf diameters, or maybe branch numbers, and maybe kernel numbers, and so on, which can be very beneficial for the future agriculture, because we have to meet the demand for the food increase in the future due to the population increase in the world. And I did some model performance of existing gene prediction models, such as GPLAB, BaseB, Run-Forest, and ALCS. And in addition to them, I also applied one graph neural network model called the graph attention network, by converting the gene interaction into one big chunk of a gene graph neural network to analyze the network. And as you can see, our model has a higher performance, or maybe at least equivalent to other existing models. But however, one big issue is that it takes a long time to compute or train this model, because it's a neural network. And there are several solutions for this, and then one solution can be the application of GPU. To check this, I just did one simple experiment by comparing two different scenarios. One scenario only uses CPU to train the model, and the second scenario uses both CPU and GPU for the training. And as you can see, it's very obvious that the training time for the scenario 2 is much shorter than the training time for the scenario 1, indicating that the use of CPU can accelerate the future agriculture in terms of speed. And then by using this, hopefully we can develop and then increase our food supply in the future. So if you're interested in genomic prediction in plants and GPUs, please have a look at my poster and let's chat. Thanks so much.
There you are. Hi, I'm Owen Bowdler. I'm a PhD student from the University of New South Wales, and my post is on the ferroelectric control of surface chemistry in bismuth ferrite in films. So what makes bismuth ferrite interesting? Well, it's composed of stacked layers of Fe2O4 2- and Bi2O2 2+, which you can see on the left there, which gives it a structural charge. Now, it's also a ferroelectric, which means we can actually move these bismuth ions. So when the bismuth ions are located close to the top surface with the Fe2O4, it actually stabilizes it. But if we move them away, we get two surfaces with an extreme charge. So we get a top surface with Fe2O4 2-, which is uncompensated, and a bottom surface with Bi2O2 2+. Each of these would rather be M2O3. So using hybrid DFT, we take a look at how the surface and the energy evolves as we move through this compositional field. So starting at point 1, over here, happy Fe2O4, it's the lowest energy structure. We polarize it into unhappy Fe2O4, where you can see there's an increase in energy to point 2, and we see a bunch of bonds breaking between the oxygen and the iron. Now, if we remove these 4 atoms, where we only have one single oxygen bond, we end up with Fe2O3 here. So we go from point 2 to 3, which takes a relatively low amount of energy to break those one single bonds compared to the energy it would take to break a double bond. From point 3 here, we can move to point 4, happy Fe2O3, which is off stoichiometry, and so that requires, again, an injection of energy. So we get to point 4 here, and then we can use that to actually adsorb oxygen. So this could be potentially used for interesting redox cycles, such as water splitting. So rather than operating at this point here, where oxygen vacancy formation is the rate limiting part of the process, we can generate a ton of vacancies at this point here, switch the material, and then consume those vacancies through the reaction. This could also be used for our battery technologies. So if you're interested, please come along and have a chat.
Cool. Hi, I'm Fiona and I'm from ANU. So the chemico-physical characterization of large molecular systems is a key challenge in computational chemistry. In computational chemistry, we have accurate approaches such as ab initio methods that can characterize molecular systems, but they exhibit quite poor scalability, like they scale of the order n to the power, that's meant to be 4, at least, where n is the system size. And also a lot of the underpinning algorithms are largely serial, so they don't take advantage of parallelism in supercomputers. And so molecular fragmentation has emerged as a strategy to reduce the formal complexity of ab initio methods to one that is linear, and also enhance algorithmic parallelizability. So fragmentation just involves taking a molecular system, breaking it up into fragments, and calculations on each of these fragments can be performed independently. And so, for instance, you could calculate the energies on each of the fragments and their interactions, stitch them together to get the energy of the total system. And so whilst this is really great, molecular fragmentation techniques aren't widely adopted, and this is primarily because most of them are done manually. There's an overwhelming lack of automation. So what we sought out to do was to develop an automated fragmentation approach. And in our approach, the fragmentation problem is recasted to a mathematical problem, which involves the optimization of a scoring function, and that's this one here. Basically, the scoring function attempts to represent the quality of a fragmentation instance, because for any molecular system, there's multiple ways you can fragment it, and we want to find the optimal way to do that. And we achieve this through the scoring function and its optimization. And so before this can happen, the molecular system is translated into a graph, and we use graph theory to identify specific regions like ring systems present, and then we fragment it, take that fragmentation instance and calculate the score with the scoring function. And this is done in an iterative procedure within an optimization procedure. And so with this automated fragmentation algorithm, we can help realize ab initio calculations of large molecular systems comprising thousands of atoms, and chemical knowledge will no longer be a prerequisite for fragmentation. If you want to learn more about this, I'm doing a poster presentation later in the session, and yeah, looking forward to that.
Right. Hi, I'm Johannes Zürk from the University of Queensland, and I'm a little bit an exception here because I'm neither young. I've been in the business for a long time, so nearly 20 years. And I haven't been using HPCs for a while, but just went into recently. And one thing I would like, though, to do is hold up the flag for data analysts, data management people here, which I assume are the minority here. And as we heard from Rick and Dan and a lot of the other people, is becoming a serial issue, especially in my domain, where we're trying to collect data, build models in order to fast-track the drug discovery process, from discovery process, development, all the way into pre-IND application. So our specialty is obviously in the antibacterial space, where we try to collect a lot of data. So I would like to emphasize once more the necessity of collecting data, and that's our exercise here, because it's really, I mean, I'm nearly tempted to suggest to extend the HPC to HPD, that we actually have something on the high-performance data community, because the HPC community is actually the only organization which brings together all the people which are using data. So, and we are lacking extreme coordination in Australia to collect all the data. We have silos all over the place. We have even data silos in the institution as well. I don't know if you ever tried to implement an electronic notebook in your organization. It's a nightmare. So we're lacking far behind to everybody else. So that's just my twist. So in more detail in a minute is basically what we are trying to break the ice with an open source data package, which we collected ourselves, combining a bit over the domain, chemoinformatics and bioinformatics, where we collected a lot of isolates from low and middle income country and proved its utility in AI models. So that's the gist of it. So once more, emphasize, guys, let's try to collect data in an organized way, so that there was only one comment on fair somewhere in the slide. So that's a buzzword at the moment, that all the data has to be fair. A lot of our data here is not even close to it. So that's my emphasis. For more details on my poster, which should be somewhere. Thank you.
Hi, I'm Fazale, the third-year PhD student of Computing School from the Australian National University. The research project is about calculating the energy of the whole molecular system by solving the Schrödinger equation. This equation is fundamental in computational chemistry and quantum mechanics. Basically, atoms in a molecule have both attraction and repulsion forces amongst them. But unfortunately, because of the Coulomb repulsion term in the Schrödinger equation, we are not able to have an exact solution for it. So even if our molecular system has 2 electrons, we can have a exact answer. So we have to go with approximation. We use the Hartree-Fock method to approximate the energy and the wave function of the of this equation. But Hartree-Fock method that we use is really accurate. It's 99% accurate. But the problem is all of these calculations are really expensive. And the computational cost of this is about n to the order of 4. So all of the researchers are working with interesting systems which has thousands of atoms. So it makes it impossible to calculate with these systems, with the traditional, Hartree-Fock methods. So we design and develop a new HPC algorithms called CPF and scale them on the exascale systems. We use the fragmentation and we are dividing the whole molecular system into several fragments, and by calculating the energy of each fragment and applying the correction, which is coming from the electrostatic potential of their surrounding, we can combine all of this energy and achieve the final energy of the system. Because of the nature of the fragmentation, we can see it has a high possibility to be parallelized, and we can reduce the computational cost to linear. If you have any questions and comments, I'm so happy to have a chat with you in the poster presentation. Thank you.
Do I just go like that? Hello, everybody. I'm Jack. I'm an undergraduate under Giuseppe Barker's lab. And so I thought today what I'd do is actually just plainly say what my problem is. And so my problem is the conformer search problem. And so in high school, often you learn about chemistry and everything is in 2D. And you've just got a graph of the molecule, you've got the bonds, and you've got the atoms, and then you try and do chemistry that way. But when we move into the computational realm, we need to go from this 2D representation into a 3-dimensional representation. So we need to map from the bonds and the atoms of a molecule into the 3D representation. And so on a large scale, this is the protein folding problem, but it's also important on a small scale, especially for drug-like molecules like ligands, where you can have multiple valid mappings from that 2D graph representation to the 3D representation. And so when solving this problem, you need to consider 2 components. The first is generating these mappings, and the second is deciding whether that mapping is good or not. And so for generating the mapping, there are many approaches. We employ a stochastic approach with a genetic algorithm, and then for evaluating whether that mapping is good or not, we use ab initio quantum energy calculations. These scale at n to the 5, so in my poster you'll see how we overcome these sort of computational challenges. The search space is exponential, and the energy calculations for determining a solution scale as n to the 5. So it's a difficult computational challenge, but it turns out with the right kind of parallelism, you can actually get stellar performance. And so my project is the first to use RIMP2 energy calculations for the conformer search problem, and as a result, it's able to get better performance than our competitors on several important benchmarks, and in fact, finds new local minima on the potential energy surface when compared to competing methods. So check out the poster for the results. Thank you very much.
Hey, my name's Brenda. When you breathe through your mouth, you can interpret that as an error warning from your body telling you 2 things. One, that maybe you're a bit stressed, maybe you have to run for the train, and also that now your body isn't benefiting from the humidification, air conditioning, and filtration of the air you're inhaling that your nasal cavity can do because you're breathing through your mouth. Short term, this error warning can be ignored and it's fine. Long term, if you are consistently breathing through your mouth, even when you're not stressed, maybe you're watching a presentation, it means that there's a lot more particles going into your airway, and that can cause damage to your respiratory problems, and it can cause more severe error warnings, such as airway infections and respiratory illnesses. So this is where normally doctors come in, and they want to deliver drugs to your airway to treat this more severe error. And that's where I come in. I'm helping with the computational fluid dynamic modeling using the Gardi HPC and modeling how particles travel into the airway and trying to modify the size and the properties of the drugs so that they can land in the places where they are needed. However, the doctors are using the same thing that is the problem. So the oral cavity as the inlet, so you can take advantage of the fact that it doesn't filter the air, so it's able to reach the airway. So what I'm trying to do with my work that is slightly less, doesn't bring in as much money, but I want to make sure that people can understand the benefits of nasal breathing by using computational fluid dynamics to show how the airway functions, and the best to your ability, breathe through your nose, and especially when you're at rest, if you're sleeping, eating, talking, you can still breathe in and out through your nose. Thank you.
With the increasing demand for high performance electronic devices, one of the problems faced is that traditional semiconductors can no longer meet requirements because electron collisions can use a lot of energies. That's reduce the working efficiency. So the two-dimensional topological insulators, which present insulating surface states, but whose edge is conducting, can provide a good platform for generating interesting electronic states. Interestingly, by introducing magnetism, it can generate a series extraordinary electronic edge states. For example, in the topological insulator with ferromagnetism, a single spin conducting edge state can be obtained, which can enable high transmission speeds without energy consumption. Besides, different magnetic configurations combined with topology can present different topological properties. So the magnetic topological materials can provide a good platform for exploring interesting topological states, which are expected to be used in the future electronic devices. However, so far only limited magnetic topological materials have been found. The synthesis and measurements in experiments are very challenging, so it makes the simulation works particularly important. So my project aims to explore new magnetic topological materials by using first principle simulations and a series of cobalt continuum materials with interesting collinear and non-collinear antiferromagnetism are predicted in my work. The results are summarized in my poster. Please feel free to discuss with me later. And I'm Ziyuan from Monash University. Thank you for your attention.
So, good morning, everyone. My name is Zachary Cook-Baldock, and I'm a PhD candidate at Flinders University in South Australia, particularly our Centre for Defence Engineering, Research and Training. So, my research group's interest is the intersection of computational fluid dynamics, submarine applications, and artificial intelligence. So, some of you may be familiar with the AUKUS Pact, or the AUKUS Agreement, which plans to bring in new conventional submarines in either the late 2030s or early 2040s. In the interim, however, Australia's current capability, the Collins-class submarine, is being phased out and is approaching its end of life. So in that interim period, it's important to fill that capability gap with new technologies, such as autonomous submarines. So you may have noticed that the vehicle in the left there doesn't look like a conventional submarine, and it's not. So that's what is determined to be an extra large autonomous or uncrewed underwater vehicle, and it's shown recovering just beneath it a smaller autonomous underwater vehicle or a drone. So these vessels carry no crew, and they're designed to undertake similar operations to our current submarine platforms, so intelligence gathering, anti-mine and anti-submarine missions. When assessing the use of these quickly and at scale, it's very important to conduct hydrodynamic modelling, so computational fluid dynamics, as you've seen some of the other presenters cover. That can be done at a workstation level, but it would be lower fidelity and the results would be significantly less meaningful. So what we've been doing is leveraging the Gardi facilities in collaboration with some other facilities to accelerate the speed of that computation using technologies such as GPU acceleration and NVIDIA's A100 cards to see performance increases or computational speed increases of about 8 to 10 times. So what I'm presenting here today is just a small subsection of that research, which is a unsteady RANS simulation of the recovery of an autonomous vehicle at its most adverse hydrodynamic point. So if you're interested in that, please feel free to come and grab me outside. I'd love to chat about it. Thank you for your time.
Good afternoon, everyone. I'm Kathy from the ANU, and I've joined Dr. Wan from the NCI for this project about NLP and also big literature data. So back when I just started my master's, I always believed that there are like perfect taxonomies and scientists always know about what is going on in each research area. And this is certainly very naive. And when I started my first systematic review, I realized how complex and how painful this could be. So it would be incredible if we have a method that could help us to get some quick insight about what is going on in a specific domain very easily. So in this project, we want to examine what is the latest development and trends in artificial intelligence. We want to try to categorize AI into different sub-areas or topics and find out what is the most impactful ones. So in order to get the big literature data, we make use of the Research Graph platform. We use the Augment API to get over 120 million of DOIs, get their metadata, and then filter them using AI-related search term. And we got hundreds of thousands of metadata from publication over the last 2 decades. And then we did the pre-processing, feature extraction, and we do the topic modeling using 3 popular algorithms, which include K-means, LDA, and also NMF. We also make use of Gardi for the storage and to accelerate the process of this data processing pipeline, since it could be very computationally expensive for this amount of data. So along the way, we have done a lot of checking, filtering, and drop off the low quality data, and we arrive at the results using publication data from over 400,000 publications related to the AI. So as a result, we have come up with the topics and the terms and the associated weights, and we have done some expert evaluation and also quantitative measures. So if you want to know more about the results and how this could impact research in different areas, please feel free to reach out to me at the poster session. And my poster is with social science, and which is right out in the hallway. Thank you very much. I'm Kathy John.
That's not you? No. Okay. Is that you? No. Cool.
Hello everyone, my name is Tong and part of the UNSW Air for Science team and also UNSW AI. So I'm also a third year PhD in School of Photovoltaic and Renewable Energy. For the past 3 years, my research focused on how to use natural language processing and the large language model to scientific domain. So from LSTM to BERT to GPT now. So let me introduce to the DARWIN. So this is a tailored GPT for science. We train with the Llama model from Meta with 6 million papers and a lot of fair data sets. So including like inorganic materials band gap, solubility of the organic compounds, and also a lot of like other interesting information, including like single phase or multi-phase of the metal. So we train all of them and make that model happen. So the reason why we did that model is that we published a paper in April is that we used GPT-3 to summarize the perovskite solar cell recipes. But the problem is that OpenAI is not open anymore. So therefore, after that, we start to train the foundation model in Australia. So there are two interesting things. So first thing is that from our 2 months, after our 2 months training, so we have been sure that our DARWIN model have better scientific answer than GPT-4. So the right answer is that, so what is the key property of the graphite carbon nitride that make it attractive material for optoelectronic applications? So the top is our answer, and the below one is the GPT-4 answer. So you could see that it's very close. And also you ask some rare compounds. So for example, what's the gap of this very rare compounds? So we can answer, but GPT says that he didn't know that. So this is the reason that because we train with a lot of papers and it knows that things, and also it can do some prediction. The other things that we find is very interesting is that it shows very strong, strong and incredible material design abilities. So what it means that is that we found that multitask training could be with our DARWIN model can predict not only the inorganic single material properties, for example, inorganic material band gaps, and also at the same time, in one model, it can predict like the organic, like a power conversion efficiency of the organic solar cell. So we group around 10 different tasks together to fine-tune our DARWIN model, and we find that the performance is even better than you train on single model, and also it's better than the SOTA model, so state-of-the-art model in that area, specifically designed for example, the Harvard OPV 15 task. Okay, so that is all my work, and also I want to share my thanks to the NCI to support my work, because we heavily use a lot of GPU resource, and also the Open Hackathon, we get 3 times faster in training now, and also happy to chat, yeah, so, and also happy to share our experience in training large transformer-based model. Yeah, that's all, thank you.
Thank you.